Algebra 2. Let's talk about Section 6 right now of Chapter 1, solving compound and absolute value inequalities. A lot of our work today is going to be what we did in Section 5, solving inequalities. But we're also going to talk about, again, what we did with absolute value equations. So all of this comes back into play. Our goal today is to solve both of these types of inequalities. So, first example, let's jump right in. Solve the inequality. I have it written right there. Graph the solution on a number line and write the solution in interval notation. Now, a note from the back of the book problems, back of the chapter problems. When I say interval notation, that is not set builder notation. The directions in the textbook will say set builder notation. I find that interval notation is more frequent and we see it a lot, so that's what I want us to use in this class. So let's solve this. 8 is less than 3y minus 7, which is less than or equal to 23. So a compound inequality, a couple different pieces going on. There's two sides of this equation with 3y minus 7 in the middle. There are two ways to solve this. The first way being you just jump right in. The key being here, there are 3 chunks to this equation. So whatever you do to one chunk, you must do to all of the chunks. So here we go. Same rules though. First thing I'm going to do is add that 7. But if I add 7 in the middle, I must add 7 on both sides as well. So I get 15 is less than 3y is less than or equal to 30. Then I'm going to divide by 3, but if I divide by 3 in the middle, I must divide by 3 on both sides as well. So my final answer is 5 is less than y is less than or equal to 10. So y is lying between 5 and 10. That's one way to do it, where you just keep it all together. The other way, if you want to be a little more organized, is you can split it apart into the 2 separate inequalities. That's one of them, with the 3y minus 7 attached with the 8. And is our keyword here. 3y minus 7 is also less than or equal to 23. Solve them both, you're going to get 5 and 10 the same way. So whichever way you prefer. For these inequalities where it's just all together, I am fine doing it this way. Keep my work nice and small. So graph this on a number line. So I'm going to draw my number line a little bit longer this time. 5 and 10 are my important numbers. Y is greater than 5. I'm kind of reading this backwards here. If y is greater than 5, I need an open circle at 5, and I'm going to be shading greater than to the right. But y is also less than or equal to 10. So at 10, filling that in, less than or equal to 10, I'm going this way. Where do the pieces meet? In the middle. You see this little barbell looking thing. This is what we call an intersection. An intersection. The place where the two branches meet. They meet in the middle. How we write this in interval notation. Remember from last video, the interval notation is the left endpoint followed by the right endpoint. We use parentheses or brackets depending on the situation. We are actually going to use both of these here. So my leftmost endpoint is 5. But 5 is not able to be my answer, so I'm going to use a parenthesis with 5. And I go all the way to the right with 10. But since 10 is a possible answer, I am going to use a bracket on that. So that is my interval notation. Let's go to another one. This one, we have 2 completely separate inequalities. They are connected with OR. So this one, we are not going to have a nice little barbell in the middle. Let's see what happens. I'm just going to solve them both separately. So this guy's a nice one-step equation. I'm just going to subtract 6. I have k is less than negative 10. And over here, I am just going to divide by 3. And I get, I'm going to go to my handy calculator here just to get the correct decimal. I have 14 divided by 3. I get 4.6 repeating. So I have k is greater than or equal to 4.6 repeating. Now, a single k value cannot be both of these things. That's why the OR is connecting them. I could have a number less than negative 10. Or I could have a number that is greater than or equal to 4.6 repeating, but I cannot have one number that does both things. So, keeping that in mind, I have my number line. My important numbers here are negative 10 and 4.6 repeating. I need to be less than negative 10, so an open circle, less than, I'm going to be shading this direction. Greater than or equal to 4.6, I need a closed dot here. 4.6 is a valid answer choice here. Greater than, I'm going to be shading to the right. So I see two separate branches going on here. So that is my number line. How do I put this in interval notation? We are going to use a symbol for union, because that's what's going on here. We call this a union. It's two separate pieces, but they are together in my answer. So here we go. We are going to do interval notation for the branch over here and for the branch over here separately, and we'll combine them together. So here's what I mean. First over here, my leftmost endpoint is negative infinity. Again, infinity is more of a concept than a number location. Therefore, I'm going to put a parenthesis on that. I can go all the way up to negative 10, but I cannot include negative 10, so I'm going to put a parenthesis there as well. With that then, when I say with that, we're going to use a U, which means union, U for union. We are going to connect to that the other branch here. I am allowed to start at 4.6. 4.6 is a valid answer. So I have a bracket at 4.6 repeating. I go all the way up to positive infinity, more of a concept than a number location, therefore we use a parenthesis. So that is my interval notation. Okay. So let's go then to some absolute value equations. Here we go. So an easy one to start, just so we know what we need to do to solve these. So if the absolute value of x is less than 3, we need to consider this. Some answers come to mind easily. I know answers like 2. If x was 2, the absolute value of 2, which is 2, is less than 3. I know that 1 is a valid answer. I know that 0 is a valid answer, things like that. But it's absolute value, meaning also numbers like negative 2, negative 1, those are valid as well. So how do I show that algebraically, especially when I need to work with more complicated situations than just the absolute value of x? So let's try this one. What we're going to do is say, well, it could be as easy as option 1, x itself is less than 3. That is a perfectly valid possibility. Or we could have x being greater than negative 3. That's when we catch these numbers there. Greater than negative 3. So this is the setup that you're going to have for all these equations. The pieces, the expression inside the absolute value bars does not change. It's just the absolute value expression. Done. First option is the same inequality symbol with the same number on the other side. But the other option is when we switch the sign and switch the sign, positive, negative sign, of the number or the expression on the other side. We did this when we worked with absolute value equations. We just didn't have to worry about the symbol in the middle. So just know that when you take the negative side, you also need to switch the inequality sign as well. We solved both of these, but this one's pretty easy. So we are just going to graph this on a number line to show what it looks like. So I am working with less than 3, but greater than or equal, or sorry, greater than negative 3, not or equal to. So negative 3 and positive 3 are my important numbers here. Less than 3, open dot at 3, less than, but x is greater than negative 3, open dot at negative 3, greater than, notice they are going to hit in the middle, so this is an intersection. I can have numbers that fit this category. I can have numbers that are both of these things. So I can consider this an and situation. I am able to be both. I am able to be both. So at this point, I want to take a break, cut the video off at this point, and go through some more examples in another video. So look out for that to continue with compound and absolute value inequalities.